So our next speaker is Zoltán Haiman, who will talk about weak lensing beyond the Gaussian machine.
Thank you for the invitation. Always a pleasure to come to Budapest. I'm going to talk about results applying machine learning to a weak lensing data set and arguing that there's more information than in the power spectrum. And then I want to talk about say something about the two leading systematics, baryons and intrinsic alignments. Before I do the science, I want to say that I spent 25 years almost at Columbia University. I recently moved to Austria, and many people ask me about this. So I want to just say 1 minute on this. This is the Institute of Science and Technology where I moved as of July 1st. This is located outside Vienna. This building used to be a mental institution, and all these buildings, it is now administration. It is actually unusually scientifically helpful. And these are new buildings. The institute is here. This is Vienna. This is the institute outside Vienna. There are no departments at this institute, but there are 5 astronomers, me and 4 others, and the institute is still growing. So there should be a few more astronomers in the next 10 years. And since I'm showing Google Maps, and I'm going so slow, I want to show one more Google Map location. This is another institute. This is a high school, which came up at dinner yesterday. This is called the Fateli Gymnasium. This is a high school. There's a plaque here, which says who went to this high school, including Eugene Wigner and John von Neumann, another Nobel Prize winner economist, and a few other illustrious people. This high school is located here. This is the hotel. You walk across here, and it's on the other side of the street. If you want to be awed by this building, you can walk there in 5 minutes. Okay. So now for the science part, the underlying questions here are that I want to answer is not just derive a particular value for omega matter or sigma 8, but how much information in principle is in a weak lensing map, and in practice can we extract this information. So this there already talks about lensing. You know that this is the large scale structure. Weak lensing is basically 0th order as a projection of this matter distribution in our line of sight direction. And the most basic way to analyze it is through correlation functions or power spectra. And this is a collection of results, not the most up to date, but I like to point out that because the effect is small, as was described previously, weak lensing distorts the shape of a galaxy from circular to roughly 1% elliptical on average. If you want to measure 1% distortion, which is systematic, of course, galaxies have eccentricities of order unity. 0.3 is just the circular, but they're randomly oriented. So you have to beat that down. You need about 1,000 galaxies to go from 0.3 to 0.01. And then if you want percent measurements of this quantity, you need 10,000 times more galaxies. So you quickly conclude you need about 10 million galaxies to do precision cosmology with weak lensing. So this became possible about 10 years ago. First, there are 4 surveys here. And what I want to emphasize in this plot is this is omega matter, this is sigma 8, this is CMB from Planck, and these are lensing results. And well, they're kind of, the sizes of their contours are comparable, still slightly larger. And also, as John emphasized, they lie below the Planck results. Of course, the future will expand this by a factor of 100, because LSST, Euclid, and Roman will be delivering billions of galaxies instead of the current value, which is about 10 to the 8. Now, the main point of this talk is that this field is not Gaussian, because this clearly doesn't look Gaussian at all. And even when you project it, you make it quite a lot more Gaussian looking. So these are lensing field maps projecting this cosmic web. And this is where I asked the audience to vote, because one of these is the lensing map. The other is a map that we generated by taking the lensing map, measuring its power spectrum, and generating a Gaussian random field. So can you tell me, raise your hand if you think, so one of these is the real lensing, the other is Gaussian. So raise your hand if you think the left one is the real lensing field. Right one? Yes, very good. So almost everybody got this right, because you can see by eye, this is different. And I think what your eye picks out is there are many more hotspots than you should have for a Gaussian random field. And well, that's actually very obvious. This is the real map, this is the mock Gaussian. And if you just take the PDF of the lensing convergence field, it's very skewed. They're very sharp drop, there are no negative huge voids. There's a large tail to high magnification in high convergence. Now, how do you get at the information that's not Gaussian? There's various approaches. This is only 30-minute talk. I don't have time to summarize, but one obvious approach is you do some perturbative expansion in real space or Fourier space. You try to measure some features you come up with, like the number density on your map of the local maxima or local minima, or Minkowski functionals. The third approach is to take the lensing field and transform it locally. Just take the log, for example, and then you get something that's actually very close to Gaussian, and you can restore some of the information. What I want to, and these approaches generally improve the error bars on cosmological parameters by maybe 50% in practice. In principle, in ideal worlds, maybe a factor of 2 or 3. What I want to talk about is machine learning. So the idea was to make simulations first. I model this signal and look at how much information is there. So just one slide on the operations. So we do n-body simulations, we do ray tracing to predict the lensing convergence, and then we make convergence maps. And we can make this in, let's say, 100 different cosmologies with different omega layer sigma 8. And we can generate thousands of realizations per cosmology. Typically, these maps are small, 3 by 3 degrees. These maps look like this. This is just, again, now to show 2 cases where W is -1 or -0.8. And you can see by eye again that there's more hotspots here than the other map, because of the structure more here. Now, the question is what you should measure on these maps, and how do you constrain cosmology? And you can, well, decided a few years ago that this is a problem in image recognition. We can try to train a network to recognize cats versus dogs. So one of these is a cat, the other is a dog. Of course, it doesn't look so different. It's more like one is a cheetah, the other is a leopard. And so it's much harder than cats and dogs, but you can do it. So what we did was we used a deep convolutional neural network. And by the way, all of this was done by Brian Liu, graduate student at Columbia. So we trained the network with many simulations, and I think I want to explain because I think most people know how neural networks work. You use many maps to train the network, and use new maps which the map hasn't seen to try to infer omega matter and sigma 8. Just how you do cosmology inference, you could take a map and you measure the power spectrum, and then you measure, and then you can use the likelihood to get confidence levels on the inference. So what we do here is these networks get actually very good in the idealized case of predicting omega matter and sigma 8. But since we have many realizations, we just treat these 2 outputs of the network as 2 numbers. And then we can determine their distribution, and we can do posteriors and likelihoods and treat the same way as a power spectrum. And this is how we do constraints. And this, in the ideal world, you get some extremely good results. So this, for example, is this is still simulation world, no noise, sigma 8 omega matter. This red contour is what you get from the power spectrum. This is the inverse area of 90. This is what you would get the green if you counted the number of peaks, which is a favorite statistic of in our group. We studied for a long time. That's in green. The blue is what this neural network can do. So about a factor of 13 improvement in area. So the first question here, the answer is that a lot more information in principle, if you really can go to this. I should emphasize we've gone to small scales of order of minutes. And in this case, the improvement is more than order of magnitude. I don't think you can do much with this as is. You can just use it as proof that somehow cosmological information exists in these maps at the high level. Now, in practice, we decided with Brian Liu to be extremely brave and apply this methodology to actual data, which of course is much more complicated. Just for convenience, because we're not part of any of these groups, we took the HSC year 1 data that's only 150 square degrees, and then we forward modeled this survey entirely as well as we could, trained CNNs on the simulations, on the forward model simulations, and applied this to the data. But this is much more complicated than what I said. This is how the data looks like. There's 19 different fields in the HSC year 1 release. So we chopped them up into 3 by 3 degree areas, and each field we did ray tracing simulations and ray tracing to the actual redshifts and positions of the actual galaxies. This is the Subaru telescope. This is Brian, who did everything. And then, of course, you have to do many steps. In this case, we have to add shape noise, which we do by taking the simulated survey, the mock survey, and randomly rotating the galaxies in 3 dimensions. And then that's basically noise. And that's how we generate noise maps. We would add photo-z errors. We have the parameterized baryonic correction model, which I'll explain in more detail in a second. We also include intrinsic alignments, which is one free parameter. So we have 5 additional free parameters. We include errors from PSF correction and shape measurement error noise. And this means we have about 3 million maps that we generated. We trained the network, and then we applied to the data. And maybe I should go faster, but basically, this is a results you get. This is a corner diagram. This is omega matter. This is capital sigma 8. And this is the amplitude of the intrinsic alignment signal. And here what you see is omega matter. This is determined more sharply than the power spectrum or from the peaks by a factor of about 2.5 in total. This is sigma 8, this is omega matter. There's a factor of 2.5 improvement. The most interesting new result is if you add the 4 additional parameters, which are characterize the baryonic effects. Now we have an additional 4 free parameters. You have a bigger corner plot. This doesn't show very well on the screen. But basically what happened here is omega matter is still determined by a factor of almost 3 better. Sigma 8 here is not improved a lot, and all the baryonic parameters are not really measured by the network is unable to pin down the baryonic parameters. But in terms of the improvements, that's actually the bottom line here. Actually, when I was in Princeton, David Spergel told me never show a table in a talk. But I mean, in this case, I want to show these numbers. So this table shows the constraints on omega matter, capital sigma 8, intrinsic alignment, different assumptions. The top line is when we have no baryonic effects. The bottom is when we let the baryon parameters free. And these parentheses are the improvement compared to the power spectrum. So these numbers here mean that we have a factor of 3 improvement in omega matter compared to the power spectrum. For sigma 8, we basically have no improvement at all. When there were no baryons, it was actually similar, but of course slightly better for the sigma 8. So the extra information by the CNN is very good still for omega matter compared to the power spectrum. And because capital sigma 8 is not improved, it means basically, again, the network is breaking degeneracies along this banana. The other very interesting conclusion, John mentioned the sigma 8 being low. In this particular exercise, the best fit value of capital sigma 8 was actually moved up quite a bit when the baryon parameters were set to be free. So the sigma 8 tension was reduced compared to Planck from 2.2 sigma to 0.4 sigma. Basically, what happened was this network, like some Pecan models, where baryons suppress the power, and then you need a bigger sigma 8 to boost it back. And therefore, the sigma 8 tension in this analysis actually went away. Clearly worth a more careful look, because our analysis is different from the actual team's analysis. We have only two cosmological parameters. The others are set at the best fit values. But still, I think this is quite natural explanation. Okay, I'm gonna skip here. And then I wanna, so the answer here is not an order of magnitude, but maybe a factor of 3 better, at least for omega, from this neural network compared to the power spectrum. So now I want to just say the two more obvious or most talked about or most important systematics is that baryons shift the mass distribution on small scales. And of course, we're extracting this information from small scales, so the baryons have to be modeled. And then the other is that when we do, we assume that intrinsically galaxies are not correlated, or if we, I didn't actually explain this, but the intrinsic alignments are put into this analysis by a model. This particular model is called a nonlinear alignment model, which assumes essentially that the intrinsic alignment power spectrum is proportional to the nonlinear matter power spectrum. And this concept works really well for the power spectrum, but it's kind of abused when you do it on the map level, pixel by pixel. So I want to say we address these two things with simulations. So here we ask the question, this so-called baryon correction model, which I'll explain in a second, is calibrated on hydro simulations, but is that good enough for the non-Gaussian statistics? And here the question is, the intrinsic alignment, in principle, the hydro simulations that you use to calibrate the baryons also predict the intrinsic alignment. So does that get captured correctly for the weak lensing statistics beyond the power spectrum? So we've analyzed everything with this particular simulation, Illustris TNG 300. Again, I assume most people know this simulation. It's an amazing public resource. It's a big box, 300 megaparsec, has high resolution. These particle masses are 7 or 8 solar masses. We use this Planck cosmology. What's crucial here for us, we have two versions publicly available, a dark matter only simulation, and then the same parameters, but hydrodynamics and star formation and geophysics. And they have 20 snapshots between 0 and 2.5, about 1 million well-resolved galaxies in the light cone in this simulation between 0 and 1 in redshift. And they have convenient halo and galaxy catalogs. So the first question is the baryon correction. So I just want to here say that, again, I assume most people have heard about this, but what you do is you take the n-body simulation, you identify every halo, and then you say, oops, my halo is not just dark matter. Actually, what happened in this halo is this used to be the profile of the halo, the NFW profile. But then there are these 4 components. Now it has hot gas sitting in the halo here. There's a central galaxy, which dominates important mass contributor in the middle. And then the gas here, these are baryons, got pushed out beyond the Viro radius by the AGN feedback. This modification is captured by 4 parameters in this model, and which are written here, which I don't think I need to go into. It's 4 physically motivated parameters. And then you take the n-body simulation and you actually manually move the particles, the n-body particles, around to match the model which are specified by these 4 parameters for every halo. And then you can ask yourself, did I accurately reproduce the hydro simulation this way? But the great thing about this approach is if you don't think you trust any of your simulations, this is quite flexible. You can change the 4 parameters. And this shows, for example, 7 different hydro simulations. So not just TNG, but from Owls, Eagle, Bahamas. These are 7 different simulations, and the points are from the simulation, and the curve are the best fit 4 parameter models that you can see actually reproduces to percent level all these simulations. So as long as these simulations capture reality, this model looks very good. You can apply it to the data, include these as free parameters and feed it. So the question we asked, okay, but this is done for the powers. If this really is the correct distribution of mass, it should also predict higher order statistics. So let's check in the hydro simulation whether that's true or not. So this is another student, Max Lee, still at Columbia. And again, the analysis is actually quite involved because he takes the illustrative simulations, he takes the halos, he modifies all of them, all of the halo profiles, and then he does ray tracing to produce lensing maps, mock lensing maps. And then you do this 2000 times so that you capture the distribution of the statistics, the posteriors of the statistics. So these 2000 ray tracings are done by taking each snapshot in the antibody and rotating and shifting it by random amounts. So these are called pseudo-independent 5 by 5 degree lensing maps. And then you can go in these maps and do whatever you like. So we measured, in this case, no machine learning, we just measured the number of peaks. I don't know why this is so blurred, but these are peak counts as a function of height in kappa. So the typical peak has a sort of RMS of 0.02 or 0.03, that's the typical kappa. Then there are many higher peaks, lower peaks. And what this shows at the bottom, which you cannot read, is that the difference between, there's a difference between the BCM corrected dark matter and the actual hydro to a level of to a degree which shown in the bottom. Maybe it's clearer here. So now we asked, we can these are the delta n over n. So the fractional difference in the number of peaks on the maps. And these are 4 different redshifts, and these are different. These error bars correspond to different surveys. I think I just should point to the bottom and show. We can read this very well. This is numbered, and we can scale these results and ask the question: are the peak count histograms in the BCM corrected antibody and the hydro statistically distinguishable or not to within X sigma? And that depends on the size of your survey and the number density of galaxies. And the bottom line is that this is DES, this is kids. They're well within 1 sigma. So when you analyze DES and kids with this model for baryons, it's indistinguishable from the hydro simulations. So that's a good thing. In the future, LSST and Roman are way bigger, and it's not enough. That means the BCM model doesn't reproduce the peak count distribution, so you have to do something else. In principle, this can be fixed by refitting the BCM model for your own statistic, but then you have to talk about whether that's fair or not, because if it's the same physical model, you shouldn't use different parameters to fit the power spectrum and the peaks. So there's more work to be done here. 2 minutes left, I think. So my last systematic was the intrinsic alignment. Maybe I'll just say that in 1 minute. This simulation illustrates is great because they also give you lots of galaxies. And you can ask if you can do mock lensing on these galaxies and ask whether intrinsic alignment was important or not. You can measure the shape of the galaxy in the simulation and pretend that you're doing an observation. Since I'm out of time, I'm just going to say this in words. What Max did was create lensing maps to the actual galaxies in the TNG simulation, including their shape measurements, pretending that we're doing a survey. And then we did the same analysis, but randomly rotated each galaxy. And then you can compare your statistic and ask, was the intrinsic alignment important? And the bottom line of this exercise is maybe here. Are the intrinsic alignment maps and the maps which are randomized and there's no intrinsic alignment, are they distinguishable? These are different non-Gaussian statistics. And the bottom line is that they're not distinguishable in a 5 by 5 degree map, But once you go above about 25 degrees, they're actually different. So that just means that the hydro-intrinsic alignment has a very large impact on any survey results that are above 25 square degrees. Again, here there are important next steps. The question I was hoping to answer by today, but we haven't got the answer yet, is the NLET, this nonlinear alignment model which people use, is that consistent with the hydro or not? And we don't yet have the answer to that. So that's it. I'm just gonna put my conclusions and thanks.
Questions?
I see interesting results. I would like to ask about interpretability. In other words, you improved it by factor 3, but could we tell what is it due to? What is it from the map? Is this the equivalent of the break point or something else that does the trick?
So that's of course a hard question, and I think we don't have a full answer. We did do a paper where we applied this technique called saliency, where the actual pixels are highlighted, where the network got most of the information for optimizing the weights. And the result from that was that most of the information is in the highest kappa and lowest kappa pixels. The kappa near signal to another 1 pixels were very unimportant. That's where the network got its information. We also can say that the network actually learns the power spectrum, but not on all scales. On intermediate scales versus small scales and large scales, the level to which the network could learn the power spectrum is actually different. But that's all I can say. I can't tell you we found particular patterns. Of course, that would be really nice to look at further.
Thank you. John?
So this stuff with the convolutional nets, I mean, the fact you're dealing with the maps at the start sounds like it's a problem that's set up just to use field level analysis. That the net will be much faster, but if you degenerate the resolution of the map, then full analysis should be fast enough to be quite feasible. And so the question is, what level of how resolution dependent is the improvement we get?
So I can show you numbers later, but as you go to arc minute, you have to go to 2-3 arc minutes to get this factor of 2 or 3 improvements. If you smooth the maps on 8 arc minutes or 6 arc minutes, you lose about half of it. So most of the information is clearly on small scales, even for the network.
Yes, I'm really surprised that you maintained your precision on the density parameter, even when you allowed for barrierification.
So I didn't say the precision actually was maintained. I just said the advantage of CNN versus power spectrum. The ratio was maintained. So things got degraded by the baryons, but the CNN still did better.
Well, but the baryons, well, in fact, it's not degenerating precision on them, it's systematically shifted. So,
but also
I'm just surprised that the additional information was still detectable, given that you were marginalizing other baryon effects.
We can go back to this table.
If the additional precision on the density parameter is coming from small scale information, then that small scale information should be erased by the uncertainty of the baryon effect.
The error bars decrease, but the advantage still remains. So I can't actually read this. I show you afterwards.
Okay, we have another question from there.
I have a question regarding the training data, and can you maybe I missed? Can you tell about the training data size?
So the simulations are typical. Oh, you mean the number of maps?
Yes, number of data points to the CNN convolution neural network.
So typically we have 100 cosmologies each cosmology has about 1,000 maps. Each map is 2,000 by 2,000 pixels. So 4 million kappa values per map.
Okay, so you have a 4 million data points to the CNF.
There are 4 million
I mean,
kappa values per map,
okay,
but there are 1,000 maps.
okay, 1,000
And
maps.
there's 100 cosmologies, so there's 100,000 maps.
Okay, so did you use any data augmentation methods in the map?
Sorry, what?
Data augmentation
Uh,
methods.
no.
Okay, thanks.
Okay, we have one more question.
More technical question. You claim that you have 1.2 million galaxies between 0 and 1. And then you had a grid, some lensing simulation and the corresponding pictures. What were the typical redshifts of those galaxies on your slide?
So the lensing kernel peaks around redshift 0.2 or something, 0.3. And I think that's where most of these galaxies are. I should say, when you do the ray tracing, you don't get all the 1 million galaxies because you do the light cone. So the boxes nearby, you have a triangle, you have a cone, and most of the galaxies are not in the cone if you have a fixed angle. So at the end, we use 500,000 galaxies, most of which are under redshift 0.2, 0.3.
I have one last question. So in the training set, you have a linear box size of 240 megaparsecs. So any larger fluctuation with larger wavelength is not resolved during the training. So my question is, when you train your data in simulation and try to fit the cosmological, find the cosmological parameters based on real observations, you will have larger ones. It's obvious the super surveillance.
Right.
So can the network mistake such a super survey with a different omega end? So you have an overdensity, and it should look like.
So I don't know. I don't have a rigorous answer to that because we haven't looked at super sample covariance. But my hunch would be probably not, because most of the information is on small scales. But yes, there could be still some residual X power. That was bigger in the box modes.
All right, thank you so much.